In this video, we'll talk about the maximum and minimum values of a function, or as we call them, extreme values of the function. So we call them extreme values of the function. Well, in particular, we'll talk about two variable functions. So we'll have that function f of x comma y. And for that function, it has a local maximum at a point a, b, if for all points x comma y, the value of the function f is less or equal to the value of the function at that point a, b, for all points x comma y that are near the point a, b. So near means that for all the points that are in the neighborhood of this a, b. So in this case, in the graph that we have, this corresponds to a local maximum of the function f of x comma y. Now, the function f of x comma y has a local minimum at a point a, b if the value of the function for the point x comma for any point x comma y is greater or equal to the value of the function at the point a, b, and this happens for all points x comma y that are near the point a, b. And in the graph, this happens here. So the value of the function at a, b is less or equal to the value of the function for any other point x comma y that is in the neighborhood of a, b. Now, the function f of x comma y has an absolute maximum at the point a, b if the value of the function f at the point x comma y is less or equal to the value of the function at that point a, b, and this happens for all points x comma y. So it doesn't matter where the point is, if it's in the neighborhood of a, b, or further away from the point a, b, if we have that f of x comma y is less or equal to f of a comma b, then we have an absolute maximum. And in this case, in the graph that we have, this is the absolute maximum. So this is the maximum value that the function takes for on all the domain of the function that it is defined. Now, the function takes has an absolute minimum at a point a, b if for all points x comma y, the value of f of x comma y is greater or equal to the value of f at the point a, b, and that happens in this at this point over here. So in this case, we have an absolute minimum, and this is the minimum value that the function takes in all the domain of where the function is defined. So let's see now a theorem on how we can find those critical points that a function has. So if the function f has a local maximum or a local minimum, and the first partial derivatives of f exist at that point a, b, where it has the local maximum and the local minimum, or the local minimum, then at that point, the partial derivatives of f with respect to x and y should be equal to 0. So we'll have to find the partial derivatives of f with respect to x and y at that point a, b, and set them equal to 0. So the point a, b is called a critical point of the function f of x comma y if the partial derivatives of f with respect to x and y at that point a, b are equal to 0. And if we remember from, if we recall, when we had a one variable function, so into this space, we had that in order to have a critical point, we should have that the derivative of f at x should be equal to 0. Now, in 3 space, we have a function f of x comma y instead, so a function of 2 variables. So we now need the fx to be equal to 0 and also the fy to be equal to 0. So in order to have a critical point. So in 2 space, in order to have a critical point, we needed the derivative of f to be equal to 0. But now we need the 2 partial derivatives of f with respect to x and y to be equal to 0. So let's apply that theorem to find the critical points of the function f of x comma y that is equal to x squared plus x times y plus y squared plus y. So the first thing, according to the theorem, is that we need to find what the fx is. So fx would be equal to derivative of x squared with respect to x is 2x, and then derivative of x times y, and then we have plus derivative of x times y, which is just y, and then the derivatives of the partial derivative of y squared and y with respect to x are equal to 0. And and then we'll have to find the partial derivative of f with respect to y, which would be equal to x plus 2y plus 1. Setting the partial derivative of f with respect to x to be equal to 0 in order to find the critical point from the theorem, we'll have that 2x plus y is equal to 0. So that means that y is equal to negative 2x. And now setting fy to be equal to 0, that gives us that x plus 2y plus 1 is equal to 0. And substituting y to be equal to negative 2x from before, so substituting y equals to negative 2x from before, we'll have that x plus 2 times negative 2x plus 1 is equal to 0. So we have x minus 4x plus 1 is equal to 0. So that means that negative 3x is equal to negative 1. And that gives us that x is equal to 1/3. And substituting for the x equals to 1/3 for when we have that y is equal to negative 2x. So we'll have negative 2 times 1/3, and that gives us negative 2/3. So the only critical point that we have, so the critical point that we have is the point with the x coordinate 1/3 and y coordinate negative 2/3. So we have only one critical point with coordinates 1/3 and negative 2/3.